the rate law. So we, before this, talked about what is chemical kinetics and how can it be expressed using a chemical reaction, how to find rate of change of a particular reaction or product, how to find the rate, and how rates are measured through 3 different techniques. Now we're going to talk about rate law. So the rate of a reaction often depends on the concentration of one or more of the reactants. As we've already seen, we notice that this effect can be done through different reactions. So, for example, if you consider that your reactant is going to products, this is a decomposition reaction, right? We're thinking that A is just going into its products. So as long as the rate of the reverse reaction in which the products would return to reactants is slow, we can ignore it. So it's negligible. So we can just look at the reactants. If the reverse of this reaction, so the products going back into reactants, is really, 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 really slow. So as long as that happens, we can always just look at the forward reaction. And we can say that the rate of this reaction is only really important to focus on in terms of the reactants, not the products. We can express the relationship between the rate of the reaction and the concentration of the reactant in terms of a rate law. So I can say that the rate is equal to concentration of my reactant times N. Now, K is a constant called the rate constant. This is a proportionality constant between the rate of a reaction and the concentration. And N is the reaction order. So whatever the exponent is tells us what type of an order of a reaction that we have. So for example, the order of a reaction is represented by the sum of the exponents of a reactant. So if you have A plus B goes to products, you would write the rate law in terms of rate is equal to your proportionality constant, your rate constant, times the concentration of A to the exponent M times the concentration of B to the exponent M. Now, N and M variables, it could be X and Y. It doesn't have to be N and M. So, the order of a reaction will be the sum of N and M. So, for example, if you have that N and M, or just N, are equal to 0, the reaction order is 0 order. And the rate is independent of the concentration. Because if you have the rate is equal to K times A, which goes to 0, taking any concentration to the exponent 0 gives you 1. So rate is just equal to the constant. So that means that the rate is independent of its concentration of the reactant. If the sum of the orders are 1, the reaction is first order, and the rate is directly proportional to the concentration of A. If rate is equal to K times A to 1, you have that they're directly related, since it's just a 1-to-1 ratio. If the sum is 2, you have a second order reaction. The rate is proportional to the square of the concentration. Rate would equal K times whatever concentration you have squared, which if we were to neglect K for just a moment, it would just be, you can see that the rate is equal to the concentration squared. So although orders are possible, including non-integer orders, these are the 3 most common. So there's other numbers that are possible, but we will only focus on these 3 most common reaction orders. So let's look at a plot of these. Reaction concentration versus time. So these 3 plots show how the concentration of A changes in time for the 3 common reaction orders with identical numerical values for the rate constant and identical initial concentrations. You can see that you have a linear line for 0 order. You have a little bit of a curve for the first and the second order reactions. So a 0 order reaction rate is equal to concentration of K, rate constant times concentration of A to 0, which would mean that rate is equal to just K. So in a zero-order reaction, the rate of the reaction is independent of the concentration. Consequently, for a zero-order reaction, the concentration of the reactant decreases linearly with time. The slope of the line is constant, indicating a constant rate. The rate is constant because the reaction does not slow down as the concentration of A decreases. Zero-order reactions occur under conditions where the amount of reactant actually available is unaffected by the change in the overall quantity. So if you think of like the sublimation process, sublimation is solid to gas. So sublimation is normally zero order because only molecules at the surface of a substance can sublime, and the concentration of the surface molecules does not change as the amount of sublimation decreases. First order reaction. So in a first order reaction, the rate of the reaction is directly proportional to the concentration of the reactant. First order, we know rate is equal to rate constant times the concentration, directly related. So for the first order reaction, the rate slows down as the reaction proceeds because the concentration of the reactant decreases. So the slope of the curve becomes less steep. The rate becomes slower with time. Second order reaction, rate is equal to the square of the concentration. It's proportional to the square of the concentration. So for a second order reaction, the rate is even more sensitive to the reactant concentration. The slope of the curve, as you can see here, flattens out more quickly than it does for the first order reaction. So the way to determine the order of a reaction can only be done experimentally. So here's a summary of everything that I just wrote. But we can determine these coefficients. We can determine these exponents through coefficients. This is only done experimentally. We can only figure out how fast or slow a reaction is going through its order by actually doing it experimentally. A common way to determine the reaction order is called the method of initial rates. In this method, the initial rate, which is the rate of a reaction during a short period of time from the beginning, is measured by running the reaction several times with different initial concentrations to then determine the effect of the concentration of the rate. So basically, you're given, I'm going to go back so I have some room here. So if you were given, for example, A to P, right? And you were trying to determine if this is first, second, or third order. And you were given this table, the concentration of A, and then the initial rate. So this was already calculated for you. There was an experiment done of calculating the rates at these initial concentrations. You have 0.1, 0.2, 0.4, 0.015, 0.030, and 0.060. So in this data set, when the concentration of A doubles, the rate doubles, what you can see. The initial rate is therefore directly proportional to the initial concentration. The reaction is therefore first order because you can see that as the time doubled, the rate doubled. As 0.2 doubled to 0.4, 0.3 doubled to 0.6. So it's directly related, so we can say the rate is equal to first order. However, we can also determine that through the method of initial rates, which would be to take the two rates over the two concentrations. So let's say that we're going to take, if this was called 1, 2, 3, we would take 0.2 for the concentration over 0.1 is equal to 0.030 divided by 0.150. And we would raise the exponent to n, since we're trying to determine n. So it's basically like we're saying that rate 2 over rate 1 is equal to K times the concentration of A at rate 2 to the power of N over K at the concentration of rate 1 to the power of N. Where then your K's would cancel and you could write the two rates over the two concentrations and solve for the exponent, which would be 1, and so you know that the order is first order. So I'm going to go over that math in a second. So it's basically using the method of initial rates. You have the data, and it doesn't matter if you choose the first or the second. You could choose the second or the third, the first or the third. It should be the same. So you would say rate 2 over rate 1 is then equal to K times the concentration of A to the N. Same for the other one. So then we do 0.03 divided by 0.015 is equal to, the K's cancel, so the 0.2 over 0.1 raised to N. So then mathematically that would be 2. So it would be 2 is equal to 2N. Well, you can use log methods to solve this. Or you could know, well, to get 2, N would have to be 1. And that's how you would solve for the order of a reaction. So just a couple little notes here about how concentration can affect rate laws. So rate laws are always determined experimentally. Reaction order is always defined in terms of reactant, not product. So the order of a reaction is always rate is equal to the rate constant times the reactants, however many you have, to the order determined experimentally, not the products, and always in terms of concentration. The order of a reactant is not related to the stoichiometric coefficient of the reactant in the balanced chemical equation. The rate constant is a proportionality constant that relates the rate and concentration at a given temperature. For first order reaction, the units of K are 1 over time. So this could be 1 over seconds or seconds to the negative 1. For second order reaction, the units of K are liters per mole time. And for zero order reactions, it's K is equal to mole over liter times the time. Now the time is written as time instead of giving you seconds, minutes, hours, because this can change depending on how fast or slow a reaction is. So let's practice this through a few problems. We looked at finding the rate of a reaction for just one reactant. Let's look at for multiple reactants. And then finding the order, looking at the overall order. So you're looking at this reaction here below, and you want to determine the rate of the reaction and the rate constant for the reaction. So again, you're only looking in terms of the concentration of the reactants. So you have their initial rates, the initial concentrations, and 4 different trials. So you want to determine the rate law. So it doesn't matter which you choose, you just choose one of them. So you can always write your rate law expression. You know, rate will equal the constant times the concentration of nitrogen dioxide raised to M times the concentration of carbon monoxide raised to N. And you're trying to find the exponents. Now, you can only find them one at a time. So we say, okay, I'm going to look at, for nitrogen dioxide, I want to have to look at when the change of carbon monoxide was 0. So basically when carbon monoxide stayed constant. So for me, when I look at experiment 1 and 2, since I'm looking at 2 different reactants, now when you just have one, it doesn't matter. But when you're looking at 2, you have to make sure that if you're solving for one of the reactants rates, the other one has to be constant. For 1 and 2, you can see that there's no change for carbon monoxide. So I'm going to look at rate 1 and 2 for nitrogen dioxide. So then I get that 0.0082 m over s is equal over 0.0021 molarity per time is equal to K times 0.2 molar m over K times 0.1 m to the m. I can then simplify this. 0.0082 divided by 0.0021 is 3.9, which will then equal to, my k's cancel, and I can simplify my exponent. 0.2 divided by 0.1 is 2, so 2 raised to n. So then you can take the log. This is another way. So you can take log 3.9, which then takes n down and gives you n log of 2. Divide both sides by log 2, and n is 1.96, which you can round to 2. This is m. So then you just figured out the order for nitrogen dioxide. So now you have to do it for carbon monoxide. Now again, you're going to look at where nitrogen dioxide was constant. Looking at this, at trial 2 and 3, nitrogen dioxide did not change. So I will use that to find the order of carbon monoxide for this reaction. So rate 3 over rate 2 is equal to the concentration of carbon monoxide at 3 raised to n over concentration at 2 raised to n. So then I get 0.0083 m over s over 0.0082 m over s is equal to 0.2 right? Then your k's cancel, you divide, you get 1.01 is equal to 2 raised to n. Then you can take the log of both sides, and then n would equal to 0.01, which you can round to 0. So therefore, your rate law is rate is equal to K times the concentration of nitrogen dioxide squared times the concentration of carbon monoxide to the 0 power, which you can simplify to say that the rate is equal to K times the concentration of nitrogen dioxide squared. So the reaction is second order for nitrogen dioxide and 0 order for carbon monoxide. Taking the 0 order would be 1, so that's why we can write it in terms of just nitrogen dioxide. So then to determine the rate constant for the reaction, we solve the rate law for K. So you would say, since rate is equal to K NO2 squared, K is equal to the rate over nitrogen dioxide squared. Now, you can use any of the 4 measurements to solve. So I'm going to choose my first one. So then I get 0.0021 meters per second divided by 0.1 molar. So I'm just using my first one. I only use nitrogen dioxide because that's in my rate law. And then I solve, and I get 0.21 meters, not meters, I'm sorry, molarity per seconds. And it's molarity to the negative 1, 2, 1. I'm going to rewrite that. 0.21 molarity second inverse. There we go. Alrighty, so then you can see that now if you had carbon monoxide, you would have also plugged in carbon monoxide. But since our rate law just had nitrogen dioxide, we just used the values for nitrogen dioxide and the rate for that experiment to find the rate constant for the specific reaction. Alrighty, let's look at this one. So write an expression for the reaction rate law and calculate the value for the rate constant K. What is the overall order of the reaction? Now this is going to be an engagement question, so I want you to try this question on your own. Exactly the way that we just solved the other one. Try this on your own and you'll submit it at the end of the day. Now here's a little homework practice. Consider the reaction described by the equation. The rate law is already determined for you. The rate constant is already determined for you. Now, using the information given, you are to fill out the missing components of the table. So basically, you're missing the initial rate concentration for your compound A, then for iodide, and the initial rate for trial 3. So how would we solve this? Okay, well, since you know that the rate law is equal to the reactants and you know the rate constant for run 1, what can you do? Well, I know that the rate is equal to 0.00117. And I know my rate constant, which is 0.00533. And I'm solving for the concentration of my first compound of A, since I don't know this, times my iodide, 0.234. So you had all your components. This is your X. You would multiply through and you find that X is equal to concentration of C2H4Br2 initial is 0.936 molar. Now what about run 2? I'm going to give you a moment to set this up on your own. Well, you know the rate, so 0.000584 is equal to the rate constant, 0.00533, times 0.234 times y, right? We don't know y. Multiply and divide, and then the y, which is the concentration of iodide, is equal to 0.468 molar. Awesome. Last one. How do we determine for run 3 the rate? Well, rate is equal to the constant, 0.00533, times 0.234 times 0.234, and that is equal to 0.000292 meters times second inverse. Awesome. So then you found your 3 components for this question. And that's how to use different rate laws and their method of initial rates to determine the orders of a reaction.